Hello, can you hear me now? Okay, it's a good news. We have small issues with my microphone. Your microphone is off. Please, all question set the question tab, and we try to answer you after we finish the presentation. Yeah, or some answer you will got during the presentation. I hope that you see my presentation. I wish to welcome all of you and thank for you wait for me for my problem. My name is Igor Krajšnik. I'm working at DV Power like test engineer. I will be your host on today's webinar. Today we will talk about transformer winding resistance measurement and a little about dissolved gas analysis. We can start now. In the first slide, we can see problem with we can find on the transformer unit. In this table, we see some basic electrical tests. A method developed through many years of testing for easier recognizing above type problem. In the third table, we can see some of advanced electrical test methods developed because of requirement of the market, and all of it is complementary with one of the basic electrical test methods. In the left corner, we can see dissolved gas analysis, and we can see that with this method we can cover almost all tests mentioned in the first table. We can parse everything but winding geometry we can test with the dissolved gas analysis. Today we will talk about winding resistance and a little bit about dissolved gas analysis. Winding resistance measurements. Why we do it for winding resistant measurements? We do it for finding winding and connection damages, partial or dead short circuit turns, broken strands, malfunction on tap changer. All we know that tap changer is only moving part on the transformer. We can measuring losing after manufacturing process. We can indirectly measure winding temperature, because when a transformer is energized, we can't measure inside temperature, but with measure resistant we can find out temperature of winding. And last is calculate winding temperature at the heat run test. Heat run test is a type test for transformer. When we do winding resistance, at first winding resistance test we can do at factory during manufacturing process and during fabric acceptance testing at installation. The risk of damage is significant every time the transformers move. Because of that, every time we move transformer, we must do winding resistance. Or at routine transformer maintenance, regular maintenance is performed in order to check the condition of the transformer units and ensure reliability. And we can measure also at unscheduled maintenance or troubleshooting after some faults. First things we need to do is do it measurement. And one of the first measures we do after fault is winding resistant measurements. Winding resistant measurement, how we do it? It is not a simple process like lookalikes. We inject DC current, we measure voltage drop, and calculate resistance. But in this equation, we see that we need to measure this R and I, but problem is with how we eliminate how eliminate the second and the third part of this equation. Second part of the equation we will eliminate with constant current. When current is stable, when current is stable, this part will be 0. Newer instruments like DV power instruments have a good hardware software capabilities to do so with ease. Bigger problem with this measurement is the third part of equation. With this part, we don't have much to do except to wait time to pass. To wait time depends from time constant of transformer. Bigger transformer have a bigger time constant. In this slide, we can see principle of measurements. What we need first to do? First, we need to saturate the transformer core. How we do it? We do it with need some energies. These steps measurements directly depends on the voltage of the testing units. Higher transformer need more energies. Because of that, one of the crucial characteristic measuring equipments for winding resistance is the compliance voltage or open circuit voltage. To simplify, instrument with higher voltage will saturate the transformer windings sooner and start the measuring. After the current becomes stable, we must wait to get stable readings. The time depends of time constant. One of the main things when we perform winding resistance measurements is how we choose appropriate current. What we need to do? We need to the red area is problematic area. If we choose current that will in this area, we would probably not be able to saturate the magnetic core, and thus the reading would be unstable. What we need to do is choose current in the green area. To avoid red area, we can use a simple rule. We need to choose current range from 1 to 6 E nominal of the winding of the rated windings, but we must must pay attention that that we don't choose a current above 10 or 15%. 10% is a recommendation by IEC. The 15% is recommendation by IEEE standard. If we choose current above this recommendation, the winding will start to heat up resistance. Because of that, we won't be able to get stable reading of the measurement resistance. In this slide, we can see two graphs. In the first graph, we can see how the resistance becomes stable during the measurements. Most users or operators make mistake. We don't wait long enough to get stable reading. How we can see that resistance at start measurement resistance is about 800 milliohms, and after 50 or 60 seconds we get stable reading. If we press or stop the measurements before 50 or 60 seconds, we will get incorrect results. Because of that, we must pay attention with this. Our instruments had appropriate algorithm who helps us to determine when resistance is stable. In the next slide, we can see what will be happened when we choose current above recommended values. This slide is show us what happens when we use 50 amps on a winding with rated current 200 amps. After we start the measuring, current will start the heating winding, and we will never got stable reading. When we do winding resistance, first question for all of us, how we speed up the measurements. In this slide, I will show you on the one simple way to speed up measurements for single phase transformer. What we need to do? We need to magnetize core in one direction and maintain that direction during the measurement process. What if we first measure from A to N, flux will be like in the picture. After that, we measure low voltage winding. We must measure from A to N that will maintain on flux orientation. In this slide is like previous slide, but I show you this principle on three-phase transformer. Like one phase transformer, if we first test A to N, second will be test N to B, and third test will be C to N to maintain flux direction. In this slide, we can see how measurement we will perform on the delta winding. It's same logic. We need to magnetize core in one direction and maintain direction during the measurements. If we first test AC, second will be best to test AB, and third test will be B from B to C. Now we will through the problem when we testing delta. Delta is problematic child when we testing because I will explain through next slides. I will try to explain through next slides. When measurement starts on the delta winding, the value of total inductance is LE in parallel with LB plus LC. Open voltage is divided through the impedance. LA impedance will have full charging voltage from measuring units, but LB and LC will only have half of the charging voltage. For that reason, phase A will be saturated faster than phase B and phase C. After the phase A becomes saturated, current will rise in phase A, voltage will drop in phase A. Sometimes we can see a stable reading, but problem stand with phase B and phase C. Phase B and phase C not yet saturated, voltage low, much lower than on the beginning measurements, and that will slow saturation from phase B and phase C. After some times, phase A is still saturated. B and C become saturated. We got voltage and current stabilized, and after sometimes we got resistance RA in parallel RB plus RC. What we can more to do to speed up measurements? One of the options is the use dual injection versus single injection. On the picture on the left side, you can see what is the flux when we when we do it with single injection. Magnetic force is lower. When we use dual injection on the right picture, we don't only faster the measurements. Magnetization will increase by factor of turns ratio. Magnetic force is much higher in this situation. We can, but in this situation we can measure two resistance simultaneously, and that will help us to faster finish the measurement process. In this slide, we will show you how we connect our instruments. I think this is RMO TD series. We need to connect one current and sense cable to one part of the transformer, and the second sense and current cables on the second part of the transformer. Set the measuring parameters, and the instrument will do it everything alone. In this slide, you can see how we can use dual injection with our single phase instruments. When we testing transformer with dual injection, we mainly can faster the measurement because all of our instrument have 3 voltage sense, and it's available to measure two windings simultaneously. Winding resistance, dual injection, high voltage and LV voltage simultaneously. DV power three-phase instruments use this method shown in this picture for overcoming problems when testing delta on low voltage side transformer. We inject half current to the outer legs of the transformer core and return it to the middle leg. After that, current will flow through the LV side. These setups help us to shorten the testing time 5 to 10 times on the large units. With these setups, we can test only low voltage side, and in this slide, I show you one more principle for dual injection on the high voltage and low voltage simultaneously. In this case, we put total current in one leg of transformer, and we need to maintain the magnetization in the same direction for low voltage and the high voltage. This is good enough for the smaller units, and with this setup you can measure two windings at the same two windings and at the same time. In this slide, you can see our new testing equipment. This is a TV400. That's it. Three-phase instruments. Your user needs only to connect the cables on the transformer. After that, he need to choose appropriate test settings, press start, and left device to do all work. With the three-phase units, measurements of all type transformer, it's much easier because the operator not need to know much things. Only he must to recognize the vector group on the transformer and set it testing parameters with it. I will show you one study case. We measure resistance on the high voltage transformer on 1 GSI units with 400 MVA and 400 kilovolts to 20 kilovolts nominal voltage. What we do on this? First measurements we will perform with our instrument with 100 amps, and you can see on the graph that after 10 minutes resistance value dropped on the 1.165, but expected value is 1.135 milliohms. It's quite a long time to get stable readings, but we use 100 amps. In this slide, you can with our three-phase instruments. I think that we do this test with our RMO40D. Use current with 25 amps and you can see on this diagram that after 4 minutes, resistance value has dropped on the expected value of 1.135 milliohms. 4 minutes and 10 minutes, it's quite a lot of difference when on this particular units. On bigger transformer, I think it's much bigger difference between a 3-phase measurement and 1-phase measurements. All our test equipments use 4-wire Kelvin measurement. 4-wire Kelvin measurement make it possible to accurately measure resistance value less than 0.1 ohms while we eliminating the resistance of the test lead wire connected. The measurement instrument to be component being measured. After we got results from winding resistance, people usually ask us, how can I decide that result they got good or bad? In this slide we show you some of recommendation and some of standards that tells us that when we finish measurement we can compare phase resistance and deviation should be less than 2% by IEEE, while SIGRE is telling us that comparison between phase the resistance value deviation should be less than 2 or 3%. Compared to the factory acceptance test result, the resistance value deviation should be less than 2 or 3%. But sometimes we must consult manufacturer of transformer and see with what transformer was be when he's made it at the factory. I need to tell something else. Without instrument, we mainly do winding resistance measurement, but in our complementary method is DV test method, dynamic resistance measurement. Why it's important? This method, DV test method, is used and approved by MR and ABB. That's its two largest manufacturer of OLTC. What we can do with this method? We can detect problems within tap changer without need to extract tap changer from the transformer. That would be a very expensive and time-consuming job. How it's performed? We inject current and recording DC current to the winding through the all operation OLTC. Change of current reflect change of resistance reactance. In this slide, outcome result of DV test is this graph. With red show DC current to the OLTC. With green we can see OLTC motor current, and with blue we show vibration. Now I will through the one tab changing process. At the beginning, when we press up or down or on regulation or OLTC, this will happen. A will moving contact from point A to R, current will drop. Next position we notice on the graph is the when moving contact short circuit these two resistors. Current will raise a little. After that, again one resistor stay in the current path. Current will low drop down. After that, when we moving contact will through the point B, and current will be stabilized at the new value of the static resistance of that position. What we can do with this graph? For every tab position or every tab change, we can analyze this graph. Our program automatically calculate transition times and ripple, and in this slide we will show you one of real tabs changer tab changer graphs. Typically, 3 parts of OLTC with 2 transition resistor will show on the saved graph. Like see on the previous slide, first is one resistor, second when 2 resistors in parallel, third is where second resistor in parallel, and this is when we stay on transition is finished and current will be stabilized. When this feature allows us to detail analyze every moving parts in the tab changer, and on some other presentation we will talk about more detailed. Now we talk some things about dissolved gas analysis. I think that we all know some things about this method. What is DGA? DGA is the single most comprehensive asset conditions assessments and management tool for oil field power transformer. Like we see on the first slide of this presentation, with DGA can detect various problems in the transformer. DGA offers advanced detection of incipient fault conditions, leading to almost all the failure models of transformer faults. And the gases that are normally measured are hydrogen, methane, ethane, ethylene, acetylene, carbon monoxide, carbon dioxide, oxygen, and nitrogen. What is the purpose of DGA? That's main purpose to provide non-instructive means to determine if a transformer incipient fault condition exists or not, to have high probability that when entering a transformer a problem is apparent, to prevent unaccepted outage, to reduce risk to the units, to the system it's connected, and to the company, and most of all the personnel monitoring that transformer. When to conduct DGA for transformer? Mainly first time we do after transformer is manufactured at the type test. After high voltage and temperature rise, test in the factory. After that, during the commissioning period, after the transformer energize, we must use take the oil sample under no load, energize with load. We do DGA before lapse of warranty period. With that, we can see that anything happened in that warranty period. 1 year, 2 year, 3 year, depends on transformer manufacturer. Used for condition-based management for predictive maintenance, and we conduct DGA after faults on transformer. Transformer main protection trip, Buchholz relay activated, pressure relay activated, differential relay activated, and during overloading. Source of gas. Gas is oil always results from the decomposition of electrical insulation materials, oil or paper, as a result of faults or chemical reaction in the equipment. Oil dissolved gases generated by oil degradation, moisture, and gas from cellulose insulation and deterioration. All we know that's function of oil in transformer. Primary functions is provide insulation and provide cooling, and sometimes help to extinguish arc, but it's not favorable condition, but used for that. In this table, you can see some of type of faults can we detect with the DGA. That will be partial discharge, discharge of low energy, discharge of high energy, thermal fault with temperature above 300 degrees, thermal fault with 300 and below 700 degrees, and T3 is thermal fault with temperature above 700 degrees. How we do evaluation of possible fault? I only mention that it exists many methods for evaluation, but there I mention this four: KGS method by IEEE, Rogers ratio method by IEEE, basic gas ratio by IEC standard, and dual triangle. It's most famous method for evaluation of possible faults. In the end of this presentation, I will show you one case study. Fault was on transformer, newer transformer to 2017. Voltage of transformer 35 kilovolts and power 6.3 MVA. What's happened with this transformer? Transformer has been withdrawn from operation. Gases began to collect in the Buchholz relay on daily basis. The staff irritated the Buchholz relay several times before deciding to withdraw the transformer from operation. After the transformer was withdrawn from operation, owner decide to do DJ in some basic measurements, winding resistance, turns ratio. And in this slide, you can see what analyze after gas DJ analyze after transformer was withdrawn. Analyze results will show us that methane is over allowable limits, and we do a double triangle analyze mark that in transformer it's T3 type thermal fault on thermal fault with higher temperature above 700 degrees. This thermal fault usually means that fault in magnetic circuit or some iron in a transformer. But after winding resistance on the high voltage side, everything seems normal. Deviation was 2.14, but on the low voltage side transformer deviation was 360%. On the phase B, turn station measurement wasn't show any problems with windings. After these results, owner decide to open transformer on the site, and after open we see that what's would be problem. Transformer has a losing contacts. Because of losing contacts, current flow through the iron shaft, and because of that we produce high temperature, probably much more 700 degrees, and lead DGA to create a T3 fault. After that, owner will remove the fault, repair the fault, complete the transformer, and we do some measurements after that. Winding resistance measurements show us that we don't have any problems with the windings, no high voltage windings, no low voltage windings. Turns ratio transformer is always good results, and after that users owner of transformer is after we finish repairing units, we do oil treatment. Why we need to do oil treatment? Because after the faults, many gases stay trapped in the oil, and we can't decide when we use next time oil. We can decide that gases from new fault, or that's the gas from the old fault. Because of that, owner do degasations, and you can see a result on this table. Every gas was in recommended by standard. This is how I prepare to talk to you, but what is the conclusion of today's webinar? Winding resistance is essential test for determination state of the current path. All other tests, for example, DV tests, are complementary and help us for assessments. Winding resistance measurement is not simple test. It's not just Ohm's law. We use only DC current for performing a test. Saturation of the core is the main thing, and at the beginning stage, higher open voltage, faster saturate test object. We must use ripple-free DC current for measurements. Delta winding is the problematic on the low, especially on the low side of big transformer. One thing that I have not mentioned is the after winding resistance test, transformer core is magnetized and needs to be returned to the original state by performing transformer demagnetizations. Like winding resistance, DGA is also one of essential measurement to assessment state of the transformer. If you have any questions, you can set on the question tab, or you can contact me at igor@dvpower.com. My colleague tells me that we have some questions.
Okay, there was one of the questions that I didn't manage to answer. Okay, so do you recommend partial discharge test for dry type transformers as a regular test? Okay, yeah, so okay, so yeah, the partial discharge test is recommended by standards for dry type transformers. So it should be, it's good to do that test even on dry type transformers. Okay, another question said, in DGA you showed why nitrogen gas is measured. Okay, so nitrogen is used as some kind of a carrier during the extraction process. So it is used to extract other gases from the oil, and that's why it is measured. So it's not used for analysis of the faults, but it simply is used as a carrier during the extraction process. Okay, another question was, as we know, the last gas we want to see is the acetylene. Some online AGD monitors set the low limit of this gas 5 parts per million. It's not that dangerous. I think, okay, we are not experts for DGA, not high level experts. As far as we know, this 5 ppm is allowed by the standards, but generally, yes, acetylene is the last you want to see. That means you have arcing in the transformer, so if sometimes it's better to watch the trend of developing gases rather than just the numbers. So if the trend is if the trend of creating acetylene is very high, if it creates acetylene in the high speed in the short time, that is the reason to be worried. Even the 5 ppm might be. And of course, sometimes acetylene is usually created in the OLTC compartment. So if it is transferred from OLTC compartment to the main tank, then it can create like a fault. You can create a false picture that there is arcing inside the transformer, but that acetylene may come from the OLTC compartment, where the arcing is usual happening. So you have arcing every time the OLTC works. So some standards are not allowing any traces of acetylene. It could be, as I said, we are not high-level experts, so but generally, whenever you have acetylene, you should definitely do some further researches. Okay, I think another question was, what about temperature rise, shutdown, hot resistance test? Is there any topic related to that? Well, that will probably be one of the topics for our future webinars. I think we haven't had a webinar about the heat run tests, so most probably we will have it in the next few months. Okay, I think we have answered all the questions up to now. But okay, as Igor said, if you have any further questions, you can write to us, either directly him on his email address or at support@dv-power.com email address, so you can contact us. Yeah, anytime. Yeah, okay. Thanks everyone for participating on this webinar, and see you again next time. Okay, one more question. Can we arrange a webinar for a practical demonstration of your equipment? Generally, we didn't do such webinars. There are some videos on our YouTube channel, on our website, so you can check. But if you want to see a practical demonstration, yeah, you can write to us on the email, and then we can see if there is a possibility to organize some kind of practical demonstration or to record some special video of some special application if you need it. Yeah. Okay. Thanks again, everyone, and see you again.
See you soon. Goodbye.